Hey guys, and welcome to lessons 3.2 and lesson 3.3. So today we're going to talk about radian measure, and we're going to talk about exact values of radians. So kind of tying into what we did yesterday, except we're going to talk about radians instead of degrees. So radians is just another way to measure angles. So just like you have centimeters and inches, there's two different ways to measure length, there's two different ways to measure angles. So radians is the second way to do it. Now, for an angle theta subtended at the center of a circle of radius r by an arc length s, the number of radians for the angle are given by this formula down here. So now let me just kind of go back and explain this a bit. So we have our angle theta here, and that's created by rotating our arm here counterclockwise to this terminal arm here. We know that the length of the arm is our radius r, and the arc length s is given by this part of the circle here, this part of the circumference of the circle. Okay, and so that's noted by s. So now to calculate the value of theta, to calculate the angle, if we know s and we know r, so if we know the arc length and we know the radius, we can just use this formula down here to calculate theta. So theta is just the arc length divided by the radius. Now, when we have an angle theta, and if we happen to have our arc length and the radius equal to each other, then theta is equal to 1 radian. Now, because the circumference of the circle is given by 2 pi r, so all the way around the circle is given by 2 pi r, so that would be the arc length, and the number of radians in a circle would be given by, now remember, we're using the formula, so theta equals 2 pi r over r, and so that tells us that the number of radians in an entire circle would be 2 pi. So if we rotate it all the way around, instead of 360 degrees, we can say that that is 2 pi radians. So since there are 360 degrees in a circle, we can say that 2 pi radians is equal to 360 degrees. And if we just wanted to know what pi was equal to, well, if we divided both sides by 2, well, then we're left with pi radians is equivalent to 180 degrees. And if we wanted to go that much further, if we wanted to know what 1 degree was equal to, well, divide both sides by 180, and then we would end up with this. So 1 degree is equal to pi over 180 radians. So in the next couple of slides, what we're going to do is convert between degrees and radians, and we're going to use this proportion here. So I guess before we go ahead and do any kind of conversion, we'll go over some key conversions that you kind of need to know and kind of come naturally after a lot of practice. So I like to start at the bottom. We already talked about 180 degrees being equal to pi radians. Now, if I wanted to know what 90 degrees was equivalent to, well, I would divide 180 by 2 to get 90. So similarly, I'll take this pi and divide by 2. So 90 degrees is equivalent to pi by 2. Again, to go from 180 degrees to 60 degrees, we divided by 3. So take your pi and divide by 3. So 60 is pi by 3. From 180 to 45, we divided by 4, so we end up with pi by 4. And then from 180 to 30, we divided by 6. So the equivalent angle in radians would be pi by 6. So again, kind of take note of these. These are, again, like I said, are just going to come naturally. Okay, so let's work on a few examples that aren't in our special triangles. So what we want to do is we want to convert the following angles, which are in radians, to degree measure. And the way we do that is you take your radian measure, and then we're going to multiply by 180 over pi. So if we start with example A, if I take this and multiply by 180 over pi, well, we can do a little bit of cross-reducing. So our pi's would cross out. And so really what you're left with is 3 times 180 divided by 2. And if you work that out on your calculator, you should get 270 degrees. Now let's try again. So negative 2 pi over 5, if we multiply by 180 over pi, again, the pi's cross out, and we are left with negative 2 times 180, and then divide by 5. And if you work that out, we end up with 72 degrees. So I remember that this is the ratio to change from radians to degrees, and the way that I remember that is that pi is on the bottom, and that will cross out the pi's. Okay, so now let's go in the other direction. Let's convert these degree angles into radian measure. So the way we do that is we are going to multiply by the opposite, or the reciprocal. This time we're going to multiply by pi over 180. So I'm going to take my 315 degrees, and I'm going to multiply by pi over 180. So if you think of this as multiplying fractions, this is really 315 over 1. We're going to do numerators times numerators, and denominators times denominators. So 1 times 180. And then all this question becomes is a fraction that you need to reduce. So reduce 315 over 180, and you should get 7 pi over 4. And that'll be our final answer. So 7 pi by 4 radians. So we'll try again. Take this negative 30 degrees, and we'll multiply by pi over 180. So again, numerators times numerators, denominators times denominators, and then you can just reduce. So negative 30 over 180 reduces to negative 1 over 6. So negative pi by 6 radians. And then finally, last example for this, 540 times pi over 180. Again, you can cross-reduce up here. You don't have to write this particular step out. But in any case, either way, you're going to reduce 540 and 180, and that reduces to just 3. So 3 pi radians. Okay, so in this next example, we want to determine the angle theta in radian and in degree measures to the nearest hundredth. And what we are told is that this arc length S, so I'll try my best to highlight here, this arc length S here is 10 centimeters, and we know that the radius of the circle is 4 centimeters. So again, remember that we started in standard position, and then we rotated counterclockwise to get theta. Now, from the first slide, we mentioned earlier that theta was equal to the arc length over the radius. So we know both of these values. We know that the arc length is 10, and we know that the radius is 4. So we can go ahead and simplify this and say that theta is, reduce this fraction, so theta is 5 over 2 radians. And another way that you can express it is in decimal form, 2.5 radians. So notice that in radian measure, you don't always need to have that pi symbol. Okay, so now let's change this 2.5 radians into degree measure. So same as the last slide, we're going to take our 2.5 and we're going to multiply by 180 over pi. Okay, and that will give us, again, numerators times numerators is 450 over pi. Now, in general, in degrees, we don't have 450 over pi degrees. So what we want to do at this point is we want to round to the nearest decimal, or sorry, to the nearest hundredth. So what we're going to do in this case, use your pi button on your calculator and go ahead and do 450 divided by pi, and what you should end up with is 143.24 degrees. Moving on, example number 4 says the pendulum of a grandfather clock is 40 centimeters long. If the end of the pendulum swings through a total distance of 15 centimeters. So imagine having a pendulum, and it swings through a distance of 15 centimeters. So let's imagine the pendulum that, let's say, starts somewhere over here, and it'll swing through and still swinging through, and then ends up somewhere down here, and then obviously swings back. So what we've done here is we've created this arc length of 15 centimeters. And again, we mentioned earlier that the pendulum is 40 centimeters long. So what the question's asking is, what is the measure in radians of the angle that the pendulum swings? So basically what we're looking for here is this angle theta that is created by this pendulum swinging. So again, we use our formula that theta equals the arc length over the radius, and again, we know that the arc length is 15, and we know that the radius created by the pendulum here is 40 centimeters. And again, just go ahead and reduce. So we end up with a fraction, 3/8 radians. And if you wanted to change that to a decimal, you could call it 0.375 radians. So now we're kind of moving on to the second part of the lesson, so the 3.3 part of the lesson, which kind of ties into what we did in yesterday's video. So what we want to do now is we want to find the exact value of these trig ratios. Now, yesterday we were given this theta here as a degree measure. Here we're given radians. So what I'm going to show you now is how to count in radians. So imagine our straight line here. We know that if we started in standard position and rotated counterclockwise to this point here, we know we have 180 degrees. And from earlier on in this lesson, we know that this value here is pi. Now, in this particular question, we are given an angle 5 pi by 6. So essentially what we want to do is we want to take this value of pi here, and we want to split it up into 6 equal sections. So I'm going to kind of roughly draw that in. So imagine this part here being split up into 6 sections. So 1, 2, 3, 4, 5, and then finally 6. Okay, so to count by pi's, all you're going to do is say, well, this first line here is 1 pi by 6. This part here would be 2 pi by 6, 3 pi by 6, and you keep going, 4 pi by 6, and this would be 5 pi by 6, and if you went all the way around, 6 pi by 6, which makes sense because if you reduce 6 pi by 6, we would get pi. Okay, so keeping that in mind, the question says find the exact value of this trig ratio. So the angle we were given here is 5 pi by 6. So I know that I'm going to start here, and I'm going to end up somewhere in the second quadrant, 5 pi by 6 radians away. Now, just like yesterday's example, so I'm just going to get rid of all these extra lines here. So just like in yesterday's example, we found where the terminal arm was, in which quadrant it was in, and we ended up dropping the perpendicular towards the x-axis, and then we needed to find this related acute angle. Well, if the entire line, the entire straight line, ended up being pi, or in this case 6 pi by 6, and our angle is actually 5 pi by 6, well, that tells me that my related acute angle must be just pi by 6. And then what we did yesterday was we used special triangles. So what I'm going to do for you now is I'm going to just create this extra page here, and we are going to convert all of those special triangles that we learned in degrees, and we're going to convert that into radians. So the first one we'll talk about is the 45, 45, 90 triangle. Now the legs of this triangle were 1 and 1, and the hypotenuse length was √2. So let's convert that into radians. Now remember from a couple of slides ago that 45 was really just pi by 4. 1 and √2. So anytime you see pi by 4, you can recognize that that is a special triangle. And the side lengths opposite of the pi by 4 are 1, and the side length opposite of the right angle is √2. So let's do the same thing for the other right triangle. Okay, so the other triangle we had 30, 60, and then 90 degrees. Now opposite of the 30, so opposite of the smallest angle was 1. Opposite of the 60 was the √3, and then finally the hypotenuse was a side length of 2. Now again, let's convert 30, 60 into radians. So 30 would be pi by 6, 60 would be pi by 3, and then we have the 90. Now, the way that I remember this special triangle is that the pi by 3 is opposite of the √3. So the 3's kind of go together. That's just kind of what I keep in my head to help me memorize. So the pi by 3 and the √3 are opposite. You could still think of pi by 6 as being the smaller angle and 1 being the smallest side. That also works. And then finally we have the side length 2. Okay, so keep these special triangles in mind, the ones with the radians, because we're going to use that in this lesson today. So, back to our example over here. We have this triangle set up right here with a related acute angle of pi by 6. Now, from our special triangles, we know that opposite of the pi by 6 is length 1. We know that this missing side, or this missing angle, must be pi by 3, so that tells me the opposite side of that is √3. And remember from yesterday's lesson that because we went left on the x-axis, I'm going to call that negative √3. And then the hypotenuse was 2. Okay, so now that we've kind of labeled our diagram here, I'm going to recall that sine is y over r, and so our y value here is 1, and our r value here is 2. So our answer to this question would be 1/2. Okay, let's try again. This time we have an angle of negative pi by 4. So again, the negative tells me we are going to rotate clockwise, and the 4, the denominator 4, tells me I need to split this measure up into 4 equal spots. So again, I'm just doing this just to kind of visually explain what's going on. So there's 1 pi by 4, 2 pi by 4, 3 pi by 4, and finally 4 pi by 4. So I took this measure here and split it into 4 equal spots. So when we are counting, I know that this here is pi by 4. So I can get rid of the rest of these lines. I just put them there to kind of illustrate how we were counting and how we get to that angle. In any case, just like every other example, we're going to take our terminal arm here and we're going to drop that perpendicular down to the x-axis, and I know that this is already our acute angle that we need to work with. So if this angle is pi by 4, then this angle must also be pi by 4, right? It's part of the special triangles. So recall the special triangles and the side lengths. Opposite of the pi by 4s were 1s. Now, we went right on the x-axis, so that stays as positive 1, but we went down on the y-axis, so I'm going to change that to a negative 1. And then remember that the radius length here would be a square root 2. Now, recall from yesterday's lesson that tan is the ratio y over x. So, take your y value of negative 1 and your x value of positive 1, and we finally get our answer of negative 1. Okay, one last example here. So I want to take my pi value and I want to split it up into 3. So based on the denominator, I'm going to take this pi and I'm going to split it up into 3. So we have 1 pi by 3, 2 pi by 3, and then 3 pi by 3 right here. That lands on the x-axis. But take a look at what we need to find. Our terminal arm needs to stop at 4 pi by 3. So I'm going to keep going, and I'm going to keep rotating, and I'm going to go one more. So 4 pi by 3 actually ends up in the third quadrant here. So 4 pi by 3 is this far away from our initial position. So again, I'm just going to get rid of all of these extra lines. I just put them there to, again, help us count. So this was 4 pi by 3. Now again, we drop down that perpendicular line, and we need to find the related acute angle. Well, again, if from initial position to the other side of the x-axis was 3 pi by 3, and our entire angle was 4 pi by 3, well then our missing related acute angle must just be 1 pi by 3. And right away, I can see special triangles. So if this angle is pi by 3, then this one must be pi by 6. And then we just start filling in the side lengths. So opposite of pi by 3 is going to be root 3. I'm going to put negative. Opposite of the pi by 6 is 1. But because we went left on the x-axis, I'm going to put negative 1. And then finally, our r value, always positive, is going to be 2 in this case. Now, again, a couple of things to remember here. Secant is the reciprocal of cosine. So if our cosine ratio was x over r, our secant ratio is going to be r over x. And now we just take our values from our diagram. So our r value is 2 and our x value is negative 1. So our final answer would just be negative 2. Okay, and then one final example, again tying into yesterday's lesson. So in that previous example, we were given the values for theta. Here we need to find the values of theta. And this kind of gives you an indication. So on a test, I will either say, find the values for theta between 0 and 2 pi, given here. So that tells me I know I must express all my answers in radians. In yesterday's lesson, I showed you a domain for theta being between 0 and 360 degrees. That would tell me I need to express my answer in degrees. Okay, so we're going to do the same thing we did yesterday. So the first thing we did was we took a look at the sign of our ratio. Now 1/2 is positive. So basically we need to determine where is cos positive. So which quadrants is cos positive? Well, remember our cast rule. Cos would be positive in the 4th quadrant, and everything is positive in the 1st quadrant. So those are our two terminal arms. So I'm going to go ahead and drop down the perpendicular lines here to create our right triangles. Now, the second thing is that we know that cos is x over r. So that tells me that the x value here is going to be 1, and then the r value is going to be 2. So this looks like the beginnings of a special triangle. What triangle has a leg of 1 and a radius of 2? Well, it's the 30, 60, 90 triangle. So that tells me, if you really wanted to write this down, that the missing side length here would be 3, or root 3. And that also tells me the missing angles. So opposite of the 1 would be pi by 6, and opposite of the root 3 would be pi by 3. Okay, and this goes for both triangles. So here is pi by 3, and here is pi by 6. So I'll just write down the second step. Okay, so we equated that x was 1 and r was 2 based on the ratio given. Okay, so now that we have our diagram set up, we are going to find the values of theta. So again, we always start in standard position and we rotate counterclockwise. So basically, we want to find the value of that purple angle. So theta 1, even just looking at the diagram, I see that the value of that purple angle must be pi by 3. Now the second one we need to find is, again, start at the initial position in standard position and we rotate counterclockwise. So this time we're going to rotate right until we hit the next terminal arm. Okay, so we want to find the value of this red angle. Now again, take a look. If we went full circle, we would have went 2 pi radians, right? Because a full circle has 2 pi radians inside. But we stopped pi by 3 radians before that. So to find the second angle, we are going to take our 2 pi and we're going to subtract pi by 3 from that. So remember, when you're subtracting fractions, you do need a common denominator. So let's imagine this over 1 for now. And if I were to change this to a denominator over 3, this would be 6 pi over 3 minus 1 pi over 3. That leaves me with 5 pi over 3. So the two possible answers for theta would be pi by 3 and 5 pi by 3. Okay, let's try one last time. Okay, so for this last example, we want to know, we're going to follow the same steps. So we want to know which quadrants is cosecant positive in. Okay, and because cosecant is the reciprocal of sine, it's the same thing as saying where is sine positive. So we can look at the first quadrant and the second quadrant based on the cast rule. And again, now we're going to determine our side lengths based on this ratio. So right now this is 2 over 1. I remember that cosecant is given by the opposite of sine, or the reciprocal of sine. So sine is y over r. This is going to be r over y. So that tells me that my radius is root 2, and our y values are 1. Okay, so again, this is the beginnings of a special triangle. Which triangle has a side length of 1 and a radius or a hypotenuse of root 2? Well, that would be the 45, 45, 90 triangle. So that tells me that this angle here is pi by 4, and so is this one. And it goes for both triangles. Now finally, you just need to determine what theta is. So start in standard position and rotate counterclockwise. So clearly the first theta here is just pi by 4. And then again, start in standard position and rotate counterclockwise till you hit the next terminal arm. So we want to find the value of that green angle. Now keep in mind, going all the way to the other side of this x-axis here would be pi radians. We stopped pi by 4 radians before that. So to find the second theta, we're going to take pi and then subtract pi by 4. And again, get that common denominator so that you can subtract, and then our final answer would be 3 pi by 4. So again, two possible values, 3 pi by 4 and pi by 4. So that's it for today's lesson. And again, if you have any questions, make sure you ask in class. Take care, guys.